Hey guys, it's Mr. Lowry. This is a in-class assignment that we did on Wednesday, 11/18. If you're in Cohort B, or sorry, for Cohort A. Cohort B, this is going to be for 11/19, which is a Thursday. We worked in pairs today to do some proofs and practice writing some proofs. And before I gave this assignment, we just practiced with a segment proof. If you haven't already seen the videos before this video in the Canvas assignment, maybe go back and watch those because those are about segment proofs. If you watch those example problems, you probably will be able to do this proof, or at least a lot of it, on your own. And that's kind of the goal, is to be able to get your way through a proof. Now, it can be kind of tricky, and if you were in class, of course, I can help you a little bit more. But since you're not in class, I'm going to try to give you some help here in case you get stuck. All right. First thing, we're just going to look at the given. So HI is congruent to TU. So that's this guy and this guy. Okay. We also know that HJ, the big segment, is congruent to TV, the big segment. So it's kind of hard to mark these congruent on the figure. I don't know yet that this is congruent to this. That's what I'm trying to prove. So I know short is congruent to short, and the long is congruent to the long. What I'm trying to show is that the medium must be congruent to the medium. So we're going to need a two-column proof. I'm just going to start that over here, using this as like just a straight edge to make a nice table. All right, so on the left side, we're going to have our statements. And on the right side, we're going to have our reasons or our justifications. Okay, step one is to list the given information. So HI, the segment, is congruent to the segment TU. And HJ, which is a segment, is congruent to TV, again, a segment. And that's given. All right. One of the things that we talked about in class recently is properties of equality and properties of congruence. So I gave you this handout here, and you can download it on the notes for a previous class if you don't have it already. But right over here we have properties of congruence, and there's only three: reflexive, symmetric, transitive. These are the same three, but just for angles. Over here, these are all the properties of equality, and notice we have all these other properties: addition and subtraction, multiplication and division, substitution, distribution. So there's more properties of equality than there are properties of congruence. Because that's the case, a lot of times what we want to do is we want to convert our congruent statements into equations. Okay, so I know that the measurement of HI is congruent to is equal to the measurement TU, and I know the measurement of HJ is equal to the measurement of TV. And so now I have fairly similar statements, here and here. The difference is these don't have lines on top of the letters, and we don't have the little swooshy over the equal sign. So these are equations, and I can do more with equations, like add and subtract and multiply and divide and substitute. The reason I can go from here to here is just it's the definition of congruent segments. Congruence means, by definition, equal measure. So I'm going to put definition of segment congruence. Okay. That's just a definition. All right, now step 3 is where it gets a little bit tricky, because step 2 follows directly from step 1, but now I need some extra information. Okay, notice what I'm given here is I'm given a short segment and a long segment and a short segment and a long segment, and I want to prove something about the medium segments. So I want a statement that kind of talks about the relationship between all three of those segments, between the short one, the medium one, and the long one, between the short, the medium, and the long. So I'm going to try to come up with some statements that have that relationship. So what I can say is that HI plus IJ is equal to HJ. That's the segment addition postulate. So if I have, this little guy here, and I add it to this little guy here, I'm going to get the length of the big one. I can say the same thing for this guy here. So I know that TU plus UV is equal to TV. Okay, again, that's the segment addition postulate. and it's in your book in section 2.7. If you're curious where that comes from, we talked about it in class. So if you're at home going through this, you may not have seen that yet, but it is in your book. Okay, now from there we can do something kind of clever. We really want to know about ij and uv, right? We want to know about these two guys. We want to show that these two guys are equal and then congruent. What we already know, though, from step 2 is that hj and tv are equal to each other. So these two guys right here, hj and tv, we already know they're equal. And I know hj is equal to this, and I know tv is equal to this. So I can rewrite this statement right here, but I'm going to replace hj with hi plus ij. So that's equivalent to hj. That has to be equal to tu plus uv. Kind of going over the line here, sorry about that. So since these are equal, I can set this equal to this. And that's what I have here. Okay, step 5. Again, what I'm trying to get is ij equal to uv. Okay, I have an equation here, and I also know from earlier that hi and tu are the same. So hi and tu, these guys are the same measurement. And so I can subtract both of these. I can subtract this measurement from both sides because it's the same thing. So if I did subtract hi on this side, subtract tu on this side, what I would get is ij equal to uv. Essentially what I'm doing is I'm saying these two combinations, and then I'm subtracting out the stuff that I already know is equal to each other, so that I just get these leftovers. So ij equals uv. We need to do a couple justifications that we missed. This one right here, number 4 that we missed, is the substitution property of equality. Substitution property of equality says I can replace this hj with what it's equal to, and I can replace this tv with what it's equal to. And so I'm using this statement along with these, and I'm substituting to get another true statement. So that's substitution. And then I'm subtracting these two guys, since they're equal measure, subtracting it from both sides, and that's the subtraction property of equality. Okay, now I'm almost where I need to be. ij is equal to uv. I want to show that segment ij is congruent to segment uv. So I'm really, really close. There's one more step that we need, so I'm just going to continue this over here. So step 6. We're going to say that segment ij is congruent to segment uv. And that's, again, the definition of congruent segments. And now we're back to where we ended up where we wanted to be. So there's a couple properties of equality here. Substitution right here and subtraction right here. Okay, we have to have equations in order to do that, and so we can't stay in with congruence. We have to transfer it to equations, then we can use all of our equation stuff, and then we transfer it back to congruence. Okay, so that's just another example of a segment proof. Okay, now this guy here is really similar. You're going to use the subtraction property of equality in this one as well. You also need this thing called the angle addition postulate. Essentially, the angle addition postulate says that if you have two angles that are next to each other, the measure of the first angle and the measure of the second angle equals the measure of the big angle. It's pretty similar to the segment addition postulate. So if you want to, you can look that up on 107. We're going to need to use that in this, so that might be helpful for you. So let's go ahead and set this one up. Okay, so I'm going to do statements and reasons here. I'll just use SNR for statements and reasons. And step 1 is going to be to start with the given information. So the measure of angle RSW equals the measure of angle TSU. So RSW and TSU. Notice that they overlap, right? RSW and TSU overlap. Okay, this is a given. All right. I want to know something about RST, which is this little guy, and WSU, which is this little guy. So we have to kind of think about the relationship between the small angles and the bigger angles, and then kind of state that relationship. So I know that angle RST plus angle TSW equals angle RSW. Actually, I should say the measure. The measure of RST plus the measure of TSW equals the measure of RSW. That's the angle addition postulate. The two small angles add up to the big angle, or the measures of the two small angles add up to the big one. So what I'm going to say here is the measure of angle RST, actually I can use that. RSW is equal to the measure of angle RST plus the measure of angle TSW. Okay. Again, the little guys add to the bigger guy. All right, that's the relationship between those two angles. I'm going to do the same thing over here. I'm given these bigger angles, RSW and TSU. I need to talk about what that angle is in relationship to the smaller ones. So I want to relate those somehow, since what I'm trying to prove is about the little ones. So I'll start with the big one again, measure of angle TSU this time, TSU, and that's equal to TSW plus WST. So TSW and then the measure of angle WST. Okay. All right, step 4 is I already know that these are equal. So I know RSW and TSU are equal, right here. RSW, TSU. So these two guys the measures are equal, which means I can set this stuff equal to this stuff. These two angles together equals these two angles together. All right, in the figure here, this angle plus this angle, I'll number them here. It'll be a little easier to talk about. Angle 1 plus angle 2 is the same measure as angle 2 plus angle 3. So I'm going to write that. I'm going to need a little bit of space, so I'm going to go down here a little bit. So the measure of angle RST plus the measure of angle TSW is equal to the measure of angle TSW plus the measure of angle WST. Kind of a long statement, so it's kind of going over. You might need a little bit more room on yours. Notice that they both have angle TSW in them, right? They overlap and they both share this same TSW angle. So these statements here both have this measure of angle TSW. We need to go back and talk about these two steps. We wrote these, but we didn't give a justification. The justification for both of these is the angle addition postulate. It's the postulate that allows us to say that the measures of the two small angles sum to the measure of the big angle. So this is another angle addition postulate. Okay, sorry, back down in step 4, we have an equation, right? We have an angle measurement and an angle measurement equal to an angle measurement plus another angle measurement. But notice they both have this in them, measure of angle TSW, that middle angle. So if I subtract out that middle angle, if I subtract this measurement from both sides of my equation, I get what I'm looking for, RST and WSU. Sorry, this should be WSU right here. WSU should be equal to each other. So you don't really show this in your steps here, but we're going to subtract the measure of angle TSW from both sides. That will leave me with the measure of angle RST equal to the measure of angle WSU. And that's what we were trying to prove. So the step from here to here is this is the substitution property. Substitution property of equality. And then I subtract from both sides. That's the subtraction property of equality. Okay, so kind of similar, because in this first proof I used also those same two justifications, substitution and then subtraction, substitution and subtraction. And you end up with the angles that you're after. So angle addition postulate to set up the relationships between the small angles and the big angles. Then substitution to make the sum of the two small angles equal to the sum of the two small angles. Subtract out the middle angle that they both have in common, and then you end up with the small angles equal to each other, which is what you wanted. So just some practice using those properties of equality within a proof. It's kind of an important skill. All right, the next one here is going to be a paragraph proof. I know paragraph proofs are kind of scary for some of you guys, but it's kind of a short proof, and I think it's just easier to write in paragraph form. So let's take a look at what we're trying to prove here. So this is the supplement theorem. It says if two angles form a linear pair, then they are supplementary. So what we're going to do is we're going to take this idea, if two angles form a linear pair, and that's going to be the given, and then we're going to try to prove then they are supplementary. So proving a theorem, we start with the if, we assume the if part, and then we have to prove the then part. We have to show that then follows from the if statement. Now we can use this figure here if we want to be able to help us. This is just a picture of a linear pair, but this is kind of what we're trying to prove. So write a proof of the supplement theorem, this theorem. We're going to use a paragraph proof. I think it's going to be the easiest. And then these are some ideas that are going to be helpful. Linear pair, opposite ray, straight angle, supplementary angles, angle addition postulate. Those are all kind of ideas that we might want to know. So this proof is actually, it's almost sometimes it's almost so obvious that it's hard to understand. But there's a few steps here that we can walk through. Let's start out with linear pair. The only thing we know right now is that angle 1 and angle 2 are a linear pair. Okay, so let's just start with that. So we are given that angle 1 and angle 2 form a linear pair. So we got to go from there. What does linear pair mean? It's two adjacent angles whose non-common side forms opposite rays. So let's add a few points here just to kind of help us out. I'm going to call this vertex A, and then I'm going to put another point down here and call this B, and I'll put another point and call this C, just so we can talk about the rays. Linear pair, the idea is the non-common sides form opposite rays. So we need to talk about those opposite rays. So we know that AC, ray AC, and ray AB are opposite rays by the definition of linear pair. That's what linear pair tells us. Definition of linear pairs. Okay? One idea that's kind of important here is that a linear pair, opposite rays basically form a straight angle. Okay, so that's kind of this opposite rays. So now we have these opposite rays forming a straight angle. So I'll say something like, since opposite rays form a straight angle, we'll say angle CAB, is a straight angle. Okay, what do we know about straight angles? Straight angles have a measurement of 180 degrees. So we'll say the measure of angle CAB equals 180 degrees, since it's a straight angle. Okay, so from there, we are going to use the segment of the angle addition postulate. By angle addition postulate, measure of angle 1 plus the measure of angle 2 equals the measure of angle CAB, because these two angles form that bigger angle. So again, angle addition postulate says the two tiny angles, the measures of the two smaller angles form the measure of the big angle. But the measure of angle CAB is equal to 180 degrees. So measure of angle 1 plus the measure of angle 2 equals 180 degrees by substitution. So angle 1 and angle 2 are supplementary. All right, so this is kind of the order. There's some words in between here, obviously, but we start with linear pair. Then we go opposite rays from there. Straight angle, 180 degrees, and then supplementary. Those are kind of the key ideas. We only know linear pair, but that gives us opposite rays from the definition of linear pair. Opposite rays give us straight angle gives us 180 degrees, and then now we have these two angles making a straight angle and adding to 180 degrees. That's supplementary. So the wording in between is a little bit tricky, and there's more than one way to order that, there's more than one way to word that, but that's kind of the basic idea. All right, last we got our vertical angles theorem. So the vertical angles theorem says if two angles are vertical angles, then they are congruent. So what we want to prove here, the theorem says that these two angles are congruent and these two angles are congruent, but that's kind of what we want to prove. So we want to write a proof of the vertical angles theorem. We're going to use this figure, and we're going to prove that that angle 2 equals angle 4. Here it says that they are, but again, this is the thing that we're trying to establish. So let's start with our T here. And let's see the hints. We want to find some linear pairs and use the supplement theorem and some properties of equality. Okay, so S and R, statements and reasons. Okay, something that's really common for students to do at this point is to just say, okay, I want to prove that angle 2 is congruent to angle 4. Okay, angle 2 is congruent to 4 because they're vertical angles. And so they try to use the vertical angles theorem to prove that these are congruent, but we can't do that because, again, the whole point of showing these are congruent is to prove this thing. We can't use a theorem in the proof of that theorem. It doesn't work. We have to use something else. So let's start with what we know. We want to talk about angle 2 and angle 4, these two guys, and we can use another angle as some help. So let's look at angle 2 and 3. Okay, so 2 and 4 are vertical angles. 2 and 3 form a linear pair, and 3 and 4 form a linear pair. So let's kind of start out with that. So we want to start with two angles being vertical angles. Remember that the if part is the given. So statement 1, if two angles are vertical angles. So we're going to say angle 2 and angle 4 are vertical angles. Okay, that's given from the figure. The way that they're drawn, they are vertical angles. So the figure, the image is kind of giving us that. All right. Step 2, we're going to talk about angle 2 and 3. So we're going to say angle 2 and angle 3 are a linear pair. Okay, now while we're at it, we can say that angle 3 and 4 are also linear pairs, because that's going to help us kind of connect 2 and 4. So angle 3 and angle 4 are a linear pair. Okay, that just comes from the figure. We know they form a straight line. All we know is line, right? These two form a line. That means they're a linear pair. So this is the definition of linear pair. Okay, well, what do we know about linear pairs? In the previous proof, we just showed that if two angles form a linear pair, then they're supplementary. So now we can use that. We just proved that theorem. We can use that theorem. So we know that they're supplementary, or in other words, the measure of angle 2 plus the measure of angle 3 equals 180 degrees. And we know that the measure of angle 3 plus the measure of angle 4 equals 180 degrees. Okay. That is going to be the supplement theorem we just proved in problem 3. Okay, so we're pretty close. They're both, these two angles together are equal to 180, and these two angles together are equal to 180. And so since they're both equal to 180, we can use a substitution here. We're going to say the measure of angle 2 plus the measure of angle 3 is equal to the measure of angle 3 plus the measure of angle 4, and that's the substitution property of equality. Okay, I'm kind of abbreviating here, but that's okay as long as we get the point across. All right, now what we want to show, what we're trying to show, is that 2 and 4 are congruent to each other. And here's 2 and here's 4. If I can get 3 out of the way, I can show the measures are equal, which means they're congruent. So what I would do is subtract the measure of angle 3 from this side, subtract the measure of angle 3 from this side, and then I would have the two angles that I want. We don't show that algebra step, we don't show like the crossing out, but the next step would be this, when we subtract measure of angle 3 from both sides. So that's going to be the subtraction property of equality. Okay, when you abbreviate, try to be clear. So substitution and subtraction both have sub in it. So don't just write sub prop because it's unclear whether that's substitution or subtraction. So I write subst for substitution and subter for subtraction, just so it's clear. Okay, now we've almost set out to prove what we wanted to. We wanted to prove measure of angle 2 is equal to measure, we wanted to prove angle 2 congruent to angle 4. We know their measures are equal, so our last step here is to just change this equation back into a congruent statement. And we do that by talking about the definition of congruent angles. Congruent angles have the same measure. So since these have the same measure, they're congruent. All right, so we did it. We started with this figure, and we didn't assume these were congruent. We assumed they were vertical, and we showed by linear pairs that they have to be congruent. Now, we could have done the same kind of proof with angle 1 and angle 3 to show that those are congruent as well. Same kind of idea, right? 1 plus 2 equals 180, 2 plus 3 equals 180. We subtract angle 2 from the middle, and we get 1 congruent to 3. So notice how this proof is really similar to this proof. Same kind of thing. There's these like overlapping angles, and you subtract out the middle angle. It's exactly what's happening here. We have 2 and 3, 3 and 4. We subtract the middle guy, we get 2 congruent to 4, which is kind of cool. So that's just kind of a rundown of the proofs we did in class. You'll probably want to, go through there and see if you can reproduce those, see if that makes sense. If you can follow the chain of logic, that's good. We're actually going to use this guy on the homework and this guy on the homework as well. So these two right here are important for your homework assignment. The next video here that I'm going to do is a video kind of getting you started on your homework. So if you need some help getting started, you can kind of check that out. Thanks for watching.